First, let us summarize what we have seen in the previous class. Okay. So we defined compatible observables. The idea is that two operators are said to be compatible if they commute, right? If their commutator is 0, so are called compatible, right? And we actually proved that compatible observables have common eigenkets, right? So compatible observables have common eigenkets. And we can label these common eigenkets using the eigenvalues of both A and B. Right? So this is the labeling that we chose. We can label the common eigenkets like this. So these eigenkets are such that A acting on ket A prime B prime is equal to A prime multiplied by ket A prime B prime, and B acting on ket A prime B prime gives you B prime multiplied by ket A prime B prime. Okay, A prime is the eigenvalue corresponding to operator A, and B prime is the eigenvalue corresponding to operator B. Okay, and we also saw that compatible observables can be simultaneously diagonalized. They can be simultaneously diagonalized. What does this mean? We know that these operators can be represented by square matrices. Okay, once we choose a basis, these operators can be represented by square matrices. Okay, when we say that they can be simultaneously diagonalized, what we mean is that we can choose a basis. Right? We can choose a basis in which the matrix representations of both A and B are diagonal. Right? So we can choose, or there exists a basis, choose a basis in which the matrix representation of A and B or compatible observable are diagonal. Right? In the same representation, the matrix, in the same basis, the matrix representation of A and B can be diagonal. Right? This is what we mean when we say that A and B or compatible observables can be simultaneously diagonalized. Okay? So I think these are the things that we discussed in the previous class. We have seen that compatible observables have simultaneous eigenkets. Actually, we have proved that compatible observables have simultaneous eigenkets. But in the proof, we implicitly assumed that there's no degeneracy. Right? We assumed that corresponding to one eigenvalue, there's only one eigenket. Right? But even though the proof is for the case where there's no degeneracy, right, where the eigenvalues are non-degenerate, this statement, right, the statement that compatible observables have simultaneous eigenkets, this statement holds. This is true even if there is an n-fold degeneracy. What do we mean by an n-fold degeneracy? If corresponding to an eigenvalue A, there are n eigenkets, then we say that the eigenvalue is n-fold degenerate. If there are two eigenkets corresponding to an eigenvalue, we said the eigenvalue is two-fold degenerate. If there are three eigenkets corresponding to the same eigenvalue, we say that the eigenvalue is three-fold degenerate, etc. Okay, so in general, if there are n eigenkets, we say that it is n-fold degenerate. All right. So mathematically, you can write the case for n-fold degeneracy like this. Okay, A acting on A prime I is equal to A prime multiplied by A prime I, and if this statement is true for I equal to 1, for I equal to 2, I equal to 3, etc. up to I equal to n, then we say that this eigenvalue is n-fold degenerate, right? Or we say that we have a situation of n-fold degeneracy. Right, so where A prime I are n mutually orthonormal eigenkets of A, all of which, or all with the same eigenvalue A prime. Okay. Now, if the n eigenkets are not orthonormal, we can of course construct an orthonormal set from it. Right, so it's possible to construct an orthonormal set out of it. Right, that's why we say that these are n mutually orthonormal eigenkets of A. Okay. So for now, you just remember that if there are a set of eigenkets which are not orthonormal in general, if there are what do you say, n degenerate eigenkets which are not orthonormal in general, okay, we can construct an orthonormal set out of it. Right? We can construct an orthonormal set of eigenkets out of this eigenkets. All right. So in general, we can say that these are. We can always, in general, consider that these eigenkets are orthonormal, because we can construct an orthonormal set from it. Now we haven't shown it here, but I think we'll be seeing it later on. So for now, we'll just consider this n eigenkets, this n degenerate eigenkets as orthonormal. All right. Now, to actually see that this statement is true in the case of n-fold degeneracy, right? We need to show that this case is, or this statement is true even in the case of n-fold degeneracy. Right? To see this, we actually need to construct appropriate linear combinations of a prime I that diagonalize the B operator. Right? What does this mean? This means that if the eigenvalue a prime is n-fold degenerate, n-fold degenerate, right? Then we can actually show that it is possible to construct linear combinations of ket ai which are eigenkets of B also. Right? It's possible to construct linear combinations of ai which are eigenkets of B also. All right. Now this is clear because if I have n eigenkets corresponding to the eigenvalue a prime, all right, then any linear combination of them is also an eigenket of a. All right. So it's important to remember that if I have, let's say that there's a threefold degeneracy, a1, a2, or let me call it as a prime 1, a prime 2, and a prime 3. Okay. Suppose these are three eigenkets corresponding to the eigenvalue a prime. All right. Then any linear combination of these eigenkets is also an eigenket corresponding to the same eigenvalue. You could take a linear combination like this, C1 a prime 1, a prime 1, okay, or let's take a linear combination like this, sum over I Ci a prime I, right? So if you take a linear combination like this, it can be seen that this linear combination is also an eigenket of A. Right? You just have to act the operator on this. So the operator will go inside. So this is sum over I Ci A acting on ket A prime I. All right. And what's A acting on ket A prime I? It is A prime multiplied by A prime I. So this is equal to sum over I Ci A prime multiplied by A prime I. Right. So here I have just considered a linear combination of all the degenerate eigenkets. Right. Now I can pull this A prime outside again. Right. So this is A prime multiplied by sum over I Ci A prime I. What does this mean? This means that if A prime I are the eigenkets of A, then any linear combination of A prime I are also eigenkets of operator A. This is something that you need to keep in mind. All right. So to prove this, actually, we don't prove it here. We'll be doing it later. To prove this statement, to prove that compatible observables have simultaneous eigenkets, all we need to do is construct appropriate linear combination of A prime I, which also diagonalize the B operator, In other words, which are also eigenkets of the B operator. All right. So if we can find appropriate linear combinations of A prime I, and if these linear combinations are also eigenkets of operator B. All right. Now these linear combinations can be chosen as the base vectors, right? And in that basis, B and A would both be diagonal. Right? That's the idea. Okay, but I think we'll be discussing the diagonalization procedure later on. Okay, this is just to give an idea. So what you need to remember from this slide is that compatible observables have simultaneous eigenkets, and this statement is true even for the case of an n-fold degeneracy, right? Even there exists an n-fold degeneracy. So this is a general statement. That's what I want you to remember. This statement is quite general, even though in our proof we used the case of non-degenerate eigenvalues, right? This statement is quite general. So we'll always say that compatible observables have simultaneous eigenkets, and this is very important when we discuss measurements. All right, and that's how that's where we'll see why these operators are actually called compatible. Okay, so even though in this slide we haven't really proven anything, I'm just stating that this statement is quite general. Right, you only need to remember that this statement is quite general. Okay. A simultaneous eigenket of A and B denoted by ket A prime B prime has the property A acting on ket A prime B prime is A prime multiplied by ket A prime B prime, and B acting on ket A prime B prime is equal to B prime multiplied by ket A prime B prime. I think we have already seen this. Okay. Now if there is no degeneracy, if there's always only one eigenget corresponding to every eigenvalue, then we don't have any particular advantage to labeling the states like this. Okay, there's no particular advantage in labeling the states like this. All right, because if we know that if the ket is given, right, and there's no degeneracy, okay, then by giving just one eigenvalue, the state is completely specified. Right? The state is completely characterized by giving just one eigenvalue. If there's no degeneracy, because we know that A acting on ket A prime is A prime multiplied by ket A prime, and B acting on ket A prime is equal to B prime multiplied by ket A prime. Okay, but the state is completely specified by just giving one eigenvalue. So the advantage, right, this notation becomes more advantageous, or it becomes more powerful when there are degeneracies, right? When there are degeneracies. So when there are degeneracies, suppose there are two eigenkets corresponding to the eigenvalue A prime. Suppose there are two eigenkets corresponding to the eigenvalue A prime, all right? Then ket A prime alone does not label the state completely, all right? So if I just say the eigenket corresponding to the eigenvalue A prime, it could be this ket or it could be the second ket. We don't know which. This is the case of twofold degeneracy that we are discussing here. Suppose the eigenvalue A prime is twofold degenerate, right? Then giving the eigenvalue of A prime or labeling the ket by the eigenvalue A prime alone, right, doesn't completely specify the state, right? It could be one of the degenerate states. It could be one of the degenerate kets, right? Then what do we do? These are the eigenvalues of operator A, or these are the eigenkets of operator A. What we do now is we'll find another operator that commutes with this operator. We'll find another operator that commutes with the operator, or we'll find another operator that's compatible with the first operator, right? Now we proved that if this condition is satisfied, then these eigenkets are also eigenkets of operator B. Right? So let's say that this eigenket is the eigenket of operator B with eigenvalue B1 or B prime, and this eigenket could be the eigenket of operator B with a different eigenvalue. All right. So these two eigenkets could have different eigenvalues for operator B. Right? Now, if I specify along with A prime, if I also give B the eigenvalue of B, then the state is completely specified. Right? Then the state is completely labeled. It's completely specified. All right. So that's why we say that if there are degeneracies, right, this notation becomes very powerful. So what have we done? In order to label the degenerate states, right, in order to label the degenerate eigenkets of A, let me write it here, to label degenerate eigenkets of A, what can we do? We can use eigenvalues, of another operator that commutes with A. We can use eigenvalues of another operator that commutes with A. Right? So in this situation, or in these kinds of situations, right, this notation becomes extremely useful. Okay. We can use a simple example to illustrate this point. Now, this is something that we have not discussed in this course, but maybe you are familiar with this from your course on elementary wave mechanics. Right? So in your undergraduate classes, you might have studied wave mechanics, and over there you might have heard of this orbital angular momentum and all that. Okay. Now, if you don't understand this, it's perfectly all right. We'll be discussing these things under orbital angular momentum algebra. All right. But if you're familiar with these things, it's well and good. Right? So there are we talked about. I think you might have talked about the eigenvalues of operators L square and Lz. Right? L square is the orbital angular momentum squared, and Lz is the z component of orbital angular momentum. Right? The eigenvalues of these operators are given by h bar square L into L plus 1, where L is an integer. All right? These are the eigenvalues of L square, and the eigenvalues of Lz are given by MLH bar, right? MLH bar, right? You might have also seen that ML can take values minus L, minus L plus 1 up to plus L, right? So ML can take values minus L plus 1, minus L plus 1, minus L plus 2, like that up to plus L. Right. Now, to characterize an orbital angular momentum state completely, it is necessary to specify both L and ML. Right. Why? Because if I say that the orbital angular momentum quantum number L is equal to 1, the state is not completely specified. All right. Because ML then could be -1, 0, or +1. Right? So if I say that L is equal to 1, the state is not completely specified because it could still be ML could still be -1, 0, or +1. So in order to specify the state completely, I have to say whether it's 1, -1, right? I have to give both these eigenvalues of L square and eigenvalues of Lz. Right? So if I give L and ML, if I say it's 1, get 1, -1, where 1 is the L value and -1 is the ML value, but then the state is completely specified. Okay, so this is a threefold degenerate state. Now, if you take L equal to 0, this is fine, all right, because there's no degeneracy. Right? L equal to 0 state, this has no degeneracy. This is what we call the S state. No degeneracy, it's fine. But if you go to L equal to 1, this is threefold degenerate. So giving only the eigenvalue of L square does not completely specify the state. Right? You also have to provide information regarding the eigenvalue of another operator. In this case, you have to give the eigenvalue of Lz. Right? Now, then the state is completely specified. Now, on the other hand, if you are saying that ML is equal to -1, for example, if you are saying ML is equal to -1, again the state is not completely specified. All right? Because in this case, L could be 1, 2, 3, 4, etc. It could be anything. L could be anything. So in order to complete the state, in order to specify the state completely, one eigenvalue is not sufficient. Right? You also have to provide one more eigenvalue. Right? So in this case, we provide the eigenvalues of L square and Lz. That would specify the state completely. All right? So only by specifying both L and ML do we succeed in uniquely characterizing the orbital angular momentum state in question. Okay, so that's an example. Now, if you don't find it completely understandable, it's fine. We'll be discussing these things later on. Okay, so let's move on. Now, often a collective index K prime is used to stand for A prime B prime. So the ket A prime B prime will often be denoted as ket K prime. Now we can generalize our considerations to a situation where there are several mutually compatible observables. Okay, there could be more than two mutually compatible observables. Okay, for example, suppose we have identified two observables which are compatible in the sense that their commutator is 0. Okay, we can look and find another. Suppose say that we can find another operator C or another observable C which commutes with both A and B. All right, and maybe we can find another observable D which commutes with all these, which commutes with A, B, and C. Okay, and if we cannot find any more observables, if we are not able to find any more observables that commute with all of these observables, then we say that we have got a maximal set of compatible observables. Then we say that we have a maximal set of compatible observables. Okay, so assume that we have found a maximal set of commuting observables. That is, we cannot add any more observables to our list without violating these commutation relations. Okay, so we are allowed to add operators to this set of commuting observables provided they commute with every observable in the set. Okay, and if we are not able to add any more, then we say that we have a maximal set of commuting observables. Right, now the eigenvalues of individual operators A, B, C, etc. Right, so these are a commuting set of observables or a compatible set of observables. Okay, so the eigenvalues of individual operators may have degeneracies. Right, maybe there are more than one eigenkets with eigenvalue A prime. Right, and then what we do is that we can specify the state by giving the eigenvalue of B also in addition to the eigenvalue of A. Right, and then still there could be some degeneracy, and then we can use the eigenvalue of a third operator to specify the state. Right, now we can continue this until the state is uniquely specified. Right, so the eigenvalues of individual operators A, B, and C may have degeneracies, but if we specify a combination A prime, B prime, C prime, then the corresponding simultaneous eigenkets of A, B, C is uniquely specified. Okay, so this is how we uniquely specify a state. We uniquely specify a state, right, or an eigenket. We uniquely specify the eigenket of a set of observables, of a set of commuting observables, by a combination of the eigenvalues of all these operators. Okay, by a combination of the eigenvalues of all these operators. So we are just using these eigenvalues to label the ket. That's all. Okay. Again, we can use a collective index k prime to stand for a prime, b prime, c prime, etc. Right? And if you are looking for orthonormality relations, we can write k prime bra k double prime ket k prime, or bracket of k double prime k prime, is equal to delta k double prime k prime. All right. This means that we get 1 only if these states are the same, if these kets are the same. Right? Now these kets are the same if all these eigenvalues are the same. Right? If all these eigenvalues are the same. So we can write the orthonormality relation like this. Bra k double prime ket k prime is equal to delta k prime k double prime. And when is k prime is equal to k double prime? We say that k prime is equal to k double prime when all these eigenvalues are equal. When a prime is equal to a double prime, when b prime is equal to b double prime, and when c prime is equal to c double prime, etc. Okay, so I think I should write delta a double prime a prime, delta b double prime b prime, and delta c double prime c prime. Okay, so this is how we can write the orthonormality relation. We can also write the completeness relation or closure. Right? So we write sum over k prime, this is sum over all states. Okay, and ket k prime bra k prime is equal to the identity operator. Okay. Now all these states are labeled by A, B, C, etc. So we have to write this as sum over all the states. So there is a summation over A prime, B prime, and C prime. Okay. So the completeness relation will look like this: sum over A prime, sum over B prime, sum over C prime, ket A prime, B prime, C prime, bra A prime, B prime, C prime is equal to 1, or the identity operator. So the completeness relation will look like this. Okay. We now consider measurements of A and B when they are compatible observables, which means that these observables commute. So when they commute, they have common eigenkets. Now suppose we measure A first and obtain a result A prime. Right? We can say that now the system is in an eigenstate of observable A. Subsequently, we may measure B and get a result B prime. Finally, we measure A again. Right? What do you expect? Now, according to our measurement formalism, the third measurement always gives A prime with certainty. Right? The same A prime that we obtained here. This means that the measurement of B does not destroy the previous information obtained in the first A measurement. Right? So we can see it as follows. Let's first revise the measurement theory a little bit. According to measurement theory, if I start with a state represented by ket alpha and make a measurement of observable A, right? So this means that I'm measuring observable A on ket alpha. The measurement result is one of the eigenvalues of A. Right? Let's say that the measurement result is one of the eigenvalues of A, which is A prime. That's what we'll get. These are real numbers. Okay. And that's not all. The state changes from ket alpha to one of the eigenkets of A. Right? So if A prime is the eigenvalue that I measured, then we can say that the state has changed from ket alpha to ket A prime. So on a measurement of observable A, the state changes from ket alpha to one of the eigenkets of this observable. Right? Now there are states that do not change. Right? Suppose if I start with an eigenket, say A double prime, right, and I measure A, there's no change in the state, I get the same state. Right? In this case, the measured value will be the corresponding eigenvalue. Let's say A double prime here. All right. So if I start with an eigenket of observable A, then the state does not change if I measure A. Right? But if I start with an arbitrary state and measure A on it, the state changes from this arbitrary ket to one of the eigenkets of this observable A. All right. So in general, states change when we carry out a measurement. All right. But there are states that do not change. If the initial state is an eigenket of the observable that you want to measure, then there is no change in state. All right. This is what the measurement theory said. Now let's look at this case. All right. Let's look at the case of compatible observables. That said, let's look at the case of compatible observables. Let's start with an arbitrary ket, an arbitrary state represented by ket alpha. And I am measuring observable A on this state. According to measurement theory, it reduces to, or it changes to, one of the eigenkets of A. All right. So this we denote, we say that ket alpha under a measurement of A changes to an eigenket of A corresponding to the eigenvalue A prime. Alright, this means that the measured value is this eigenvalue. Okay. Now, if A commutator of A and B is equal to 0, right, and let's say that they are non-degenerate, alright, let's say that all the eigenvalues are non-degenerate. Okay, so in that case, this eigenket of operator A is also an eigenket of operator B, right? Because we said that if two operators are compatible, if two operators commute, then they have common eigenkets, right? So I made a measurement of observable A. It has changed to an eigenket of operator A, but this eigenket of operator A is also an eigenket of operator B. That's the theorem that we proved. This means that this is also an eigenket of operator B, let's say corresponding to the eigenvalue B prime. Right? So state has changed to an eigenket of A, which is also an eigenket of B. Right? Now what happens if I make a measurement of B on this state? Right? Now this is already an eigenket of B, so there's no change in state. There's no change in state. The state remains get A prime B prime. Alright. Now this is an eigenket of B, so it does not change. But now this is also an eigenket of A, as we said before. So if I make a measurement of A on this state, right? If I make a measurement of A on this state, this is already an eigenket of A, so there's no change of state again. Alright. Again you get A prime, or again the state remains in get A prime B prime. So if the state remains in get A prime B prime, that means that the measured value is A prime. Right? The measured values are eigenvalues. So in the first measurement of observable A on get alpha, let's say that I got an eigenvalue A prime. On the second measurement of B, let's say that we get an eigenvalue B prime. Right? Now this state, we are making the measurement after the B measurement. Alright, and what am I going to get? I'm going to get this eigenvalue here. I get the eigenvalue A prime. So here I got an eigenvalue A prime. The B measurement has not changed this information. Right? Has not changed the state. Right? I still get eigenvalue A prime on the third measurement. Right? So it's the first measurement, second measurement, and third measurement. Right? In the first measurement, I measured and I obtained an eigenvalue A prime. Okay. Second measurement is the B measurement. Let's say that I got an eigenvalue B prime. Now on the same state, I'm measuring A and I'm going to get A prime again. Right? This is just applying the measurement theory. This means that the information is not lost. Right? So the measurement of A and B are not incompatible. The measurement of B does not destroy previous information regarding A. Right? The measurement of B does not destroy any previous information regarding observable A. Alright. Now we have discussed the spin case. Alright. We can also look at the spin case if you want to. Right. So over there, we have actually seen that the commutator of Sx and Sy is not equal to 0. This means that these are not compatible. But these are not compatible. In this case, we know that this information actually changes. Alright. Let's say Sx with Sz is not equal to 0. Now we have seen the Stern-Gerlach experiment. Okay. Let's discuss this so that we can put things in context a little bit. Right? Suppose I have got a beam of silver atoms represented by some arbitrary get alpha. Okay. Now I make a measurement Sz on it. I make a measurement of the Z component of spin. We know that there are two possibilities. Okay. We could either get eigenvalue plus h bar by 2 or we could get eigenvalue minus h bar by 2. In this case, we say that the state is Sz plus and the state here is Sz minus. Right. So the first measurement is done and the state has changed. Right. Now suppose I'm taking this state and making a measurement of Sz on this again. Right? Now we know that since this is already an eigenket of Sz, there's no change in state. So I'll get the same state again and I'll measure plus h bar by 2 again. Alright, not minus h bar by 2. I'll always measure plus h bar by 2 with probability 1. Alright. So this state is characterized by a definite Z component of spin. Alright, this is characterized by a definite Z component of spin. Okay, or a definite value for Sz. Alright. Okay, now as long as I don't make any other measurements, as long as I keep measuring Sz, I'm always going to get h bar by 2. Right? Now, for some reason, if I choose to measure Sx on it, the x component of spin of the atoms characterized by this state. Right? From the Stern-Gerlach experiment, we saw that if I make a measurement of Sx, there are two possibilities. Okay, you could either get Sx plus or you could get Sx minus. All right, these are two possibilities. Right? Suppose I got Sx plus. Suppose I get Sx plus. All right, we are starting with just one single state. First, I made a measurement of Sz, and I am checking by making more measurements of Sz, and I'm always getting plus h bar by 2. Right? Now I made a measurement of Sx. Let's say that I got a value plus h bar by 2. That means that the state has changed to get Sx plus. All right. Now, if I make a measurement of Sz on this state, again, we'll see that there are two possibilities. I could either get plus h bar by 2 or minus h bar by 2. Okay, if I get plus h bar by 2, I'll say that the system has changed to Sz plus. If I get minus h bar by 2, I'll say that the state has changed to Sz minus. All right. So here what has happened? Here what has happened is that as long as I am measuring Z, I am always getting h bar by 2 plus h bar by 2, right? The measurement of Sx on this state, right? The measurement of Sx on this state changes the state into, let's say, get Sx plus, right? Now the previous information is lost. What was the previous information? The previous information was that this state is characterized by a definite Z component of spin, right? Once I make a measurement of Sx, this information is lost, and this beam after the measurement of Sx is no more characterized by a definite Z component of spin. All right, it could either be plus h bar by 2 or minus h bar by 2. All right, so the information is lost here. Okay, so this is the case where the observables are not compatible. This is the case where the observables are not compatible. Here, what we have discussed is the case of compatible observables. So I think it's easier to compare these two cases. If the observables are compatible, right, then the measurement of one observable does not destroy any information regarding the other observable. It does not destroy any previous information regarding the other observable. Right? So here the B measurement does not destroy any previous information regarding observable A. Okay? But here, when they are not compatible, you will see that the measurement of Sx destroys any information that was already there regarding the observable Sz. Right? So any information regarding observable Sz is lost, and then again it becomes spread out. So this is what's happening. Okay, hope this is clear. So this is why this compatible observables and the discussion is important for quantum mechanics. All right, we see it in the case of measurements, because measurements always change states in quantum mechanics. Right? But if you're making measurements of compatible observables, then the information is not lost. Right? It does not change. We can say this is the reason why we say that when observables A and B commute, they are compatible. They are compatible. They are compatible in the sense that if I make a measurement of A, you don't lose any information regarding B. Similarly, if I make a measurement of B, the information regarding A is also not lost. Okay, this is the reason why we say that these are compatible. These measurements are compatible with each other. Okay, all right. Now, when there is degeneracy, the argument is a little bit more involved, but it's easy to understand. So after the first A measurement, which yields A prime, the system is thrown into some linear combination. All right. So the thing is that I'm taking a ket alpha, I'm taking a state represented by ket alpha, and I'm making a measurement of observable A. All right. We know that if we get an eigenvalue A prime, we know that the resultant state, all right, or the state after the measurement is an eigenket corresponding to this eigenvalue. It is an eigenket corresponding to this eigenvalue. Right? But we don't know which one, because there are more than one eigenkets corresponding to this eigenvalue. That's why we say that there's degeneracy. So if this eigenvalue is degenerate, we don't know in which eigenket it is. Right? So we can label these states by the eigenvalues of another operator, and we can say that after the measurement of A, it is in some linear combination. Right? Let's say that we got eigenvalue A prime. We can only say that the resultant state is a linear combination of the eigenkets corresponding to A prime. So because there are more than one eigenkets corresponding to A prime, we cannot say exactly what it is. We can say that it is some linear combination of all the eigenkets corresponding to A prime. Right? So we can write the measurement after the first measurement. Let's say that we got a measurement result A prime. right? Then we can say that the state after measurement is a linear combination of all the eigenkets corresponding to this eigenvalue. Right now, these eigenkets can be labeled by the eigenvalues of different operator, a compatible operator. Right? Let's say that these are labeled by Bi. So we can say that after the measurement, it is in a state which is a linear combination of all these kets. Right? Because we have got A prime B1, that is one ket with eigenvalue A prime. There's another let's say there's another ket with the same eigenvalue A prime B2. Right? There's another ket with the same eigenvalue, which can be denoted as A prime B3. These are all eigenkets corresponding to the same eigenvalue A prime. Right? So we can say that after the measurement, it is in a superposition. It's in a linear combination of all these eigenkets. Right? Okay. Now, well, here the n is the degree of degeneracy, and here what we have done is that we have taken a linear combination of all the eigenkets corresponding to the eigenvalue A prime. Okay, that's what this summation means. All right. So there's a sum over I here, and I actually labels different eigenkets corresponding to the eigenvalue A prime. Right? Or Bi labels different eigenkets corresponding to the eigenvalue A prime. Right? So Bi we have seen are the eigen values of the observable B. All right, which is compatible with A, right, which is compatible with A. So that's the idea. Now, where n is the degree of degeneracy and the kets A prime Bi all have the same eigenvalue A prime as far as the operator A is concerned. Right? Now we can make a second measurement. The second measurement is of observable B. Okay. Now these are a collection of eigenkets of operator B. Right? These are what is a linear combination of eigenkets of operator B. So if I make a measurement of B, what happens is that it will reduce to one of the eigenkets of B, one of the eigenkets of operator B. That's measurement theory, right? So let's say that when I make measurement of B on this state, it reduces to, now this is a linear combination, it will reduce to a definite eigenket of operator B. Okay, that's measurement theory. Let's say that it reduces to get A prime B2 or something, all right? Get A prime B2. So this means that the measured eigenvalue is B2. Now what happens if I make a third measurement of observable A here? If I make a third measurement of observable A, this is still an eigenket of operator A. So what I'm going to get is the eigenvalue A prime. Right? This is still an eigenket of operator A. So there's no change in the state of the system by measuring observable A on this system. Okay. So this means that I'll again get A prime. So what happened? The measurement of B has not destroyed the previous information that this is a state with a definite value of observable A, definite value for observable A. All right, so this state is a state with a definite value for observable A, and the measurement of B has not destroyed this information. The second B measurement may select just one of the terms in the linear combination, say A prime Bj. Okay, this means that I have measured Bj for the observable B. All right, but the third A measurement applied to this ket again yields A prime. Why? Because this is already in an eigenket of observable A. There's no change, so I'll again get A prime. Now, whether or not there's degeneracy, A measurements and B measurements do not interfere, right? They don't spoil each other. We can talk about A and B at the same time. Okay, that's why we say that A and B are compatible observables. Okay, that's why we say that A and B are compatible observables. Okay, we talked about compatible observables. Okay, compatible observables are those which commute. Right, so we say that compatible observables have common eigenkets, which is very important. Common eigenkets. So the eigenket of A will be an eigenket of B. All right. Now we said that there could be degeneracies. In that case, we can talk about a maximal set of compatible observables. Right, and the eigenvalues of these compatible observables can be used to label a state completely. Right? For example, I could label a state like this: A prime, B prime, C prime, D prime, etc. Okay, these are eigenvalues of compatible observables. Right? So if a state is not completely specified, if the state is not completely specified, by the eigenvalue of an operator A. Right? We look for another operator that commutes with this operator. Right? If there's degeneracy, we look for another operator that commutes with this operator or with this observable. Right? Then we try to label the state using both these eigenvalues. All right? Now, if again this does not fix the problem, if there is still some degeneracy left, we can look for another operator that commutes with both A and B, right? And then we can denote the state, or we can represent the state, we can specify the state, we can label the state using the eigenvalues of all these three observables, all right? Now, again, if there is some degeneracy left, we can look for another operator, all right, and use its eigenvalue also to label the get, or label a state. All right. Now, if I cannot add one more operator, if I am not able to add one more operator that commutes with all of these, right? If I am not able to add one more operator that commutes with all of this, then we say that we have a maximal set of compatible observables. So we need a maximal set of compatible observables to represent or specify states completely. We have seen the example of orbital angular momentum. Okay. Then we talked about measurements, and then we understood why these are called compatible observables. And in the measurement theory, based on measurement theory, we saw that the measurement of B, for example, does not destroy any previous information of A. So if you have a state which is an eigenket of A, which is also an eigenket of B, right? I could make a measurement of observable B here, and it does not destroy the previous information corresponding the eigenvalue A prime. Right? So if I make a measurement of A here, I'll again get the eigenvalue A prime. I'll again get the eigenvalue A prime. Right? So these, what do you say, these measurements do not destroy previous information of each other. Okay, that's why we call them as compatible observables. And when does this happen? When their commutator is 0. Right? So these are the things that we discussed so far. Okay. So with that, I think we'll conclude our discussion of compatible observables for the moment. Thank you.